So let's get started. So starting from the last lecture, we start to talk about essentially database systems, right? Instead of using it as a user, we start to think about actually how to build it as a developer. So when we talk about computer systems, right, one difference compared with the thing that we are talking about before Easter is you are going to have a whole bunch of details of system design. So often to think about that is not to think about the design itself, but really try to start from two fundamental assumptions. Your assumption on the workload and your assumption on the infrastructure that's serving that workload. So you should think about the design of the system, the thing we are going to talk about in the next couple of lectures, as the natural consequence of the assumption you have on the workload and on the infrastructure. When you are doing computer system research, right, so if you look at what database people are doing in the last half a century, is people keep revisit these different assumptions on workload. Maybe you start to do machine learning, start to do graph databases, right? You have different type of workloads, and then you have different type of infrastructure. There are new type of hardware being invented every single day. Given different assumptions, you have a different natural design of the system. So what are the workloads that we are going to focus on in this course? The workload we are going to talk about is essentially a relational database system. That is, the user is going to issue relational queries to the system. So whenever the user wants to create a table, right, so system is going to create a table on the hard drive. Whenever the user issue, for example, one SQL query, the goal of the system is try to bring the data from the hard drive all the way to you as a user and return that as a relation. And the goal is really try to understand how can we build a system that the user doesn't need to worry too much about how this query answering process is being conducted. So this is our workload. And what is our assumption on the infrastructure? In this course, we are going to focus on essentially a very simplistic view of the infrastructure. We will be focused on this storage hierarchy. That is, your data is being stored. Okay, so that is your data being stored on the hard drive. The assumption we have is you have this three-level hierarchy. At the top, there's your CPU. Can do things really fast, okay? So every single nanosecond, we are talking about is couple CPU cycles, and for every single CPU cycle, I mean, at least it can do one operation. Often it can do even more, like 10 operations to SIMD correctly, right? So it's a very fast processor at the top. And then in the middle, there is your main memory. It's slower, okay? So like sometimes when you kind of have access to the main memory, bring data, we are talking about like 60 cycles, something like that. And then your data is being stored on hard drive, right? Whenever I'm trying to like get something from hard drive, I'm talking about at a million level cycle, something like that. So this is our basic assumption on the infrastructure. So essentially the game that we are going to play in building a database system, a very simplistic one in this course, is really try to understand how can we optimize the I/O behavior between the hard drive and the main memory and your CPU to make sure we can keep the CPU busy. So that is the game we are going to play. And we also talk about this layer-wise structure of a simplistic database system, right? So at the bottom, you have your data being stored as a whole bunch of files, right, inside your file system. And at the top, the functionality you are going to provide is that you take as input the SQL query and give back the result as a relation. So at the bottom layer, right, so there's a disk manager, right, try to manage your storage, manage your disk. And then you have a buffer manager, right, to give all the upper layer the illusion that your data is actually in memory, try to abstract out the existence of the disk. Then you have access method, then you have this operator execution layer. You start to have those relational algebra operators. And then there's a query optimization layer, right? Try to take as input the SQL query, output a relational algebra tree that you can actually run. So in the last lecture, right, so we talk about this disk manager. Essentially, it's try to interact with your hard drive. It's allocate pages, right, delete pages, find the record, all those type of things, right? So the goal is all the other layers above it will not interact with your hard drive, with your disk directly. So that's the goal. So to make that happen, there are actually multiple things that we are curious about. That is, given a single relation on the left-hand side, how can we organize it as a file, or which is a collection of pages? We want to have page because whenever I'm fetching information from my hard drive, it's faster for me to fetch a block because of the seek rotate structure that we talked about last time. How to organize this relation as a file? And then inside each page of this file, how can we organize information within a page, which is a collection of tuples. Each tuple corresponds to a single row in this relation. And also, how can we organize the structure of a single tuple? So this is what we talked about last time. So today, we are going to move essentially one layer up. Now we know how to interact with the hard drive. So now, essentially, you are the buffer manager now, right? You will not touch the hard drive. That thing doesn't exist, right? Like for you. All you can do is just interact with the disk manager. But then, let's try to think about how to build a buffer pool manager. And also, we are going to, I think we have time to go another layer up today to talk about the access method. So what do we want to do in a buffer manager? So essentially, the goal of the buffer manager is really try to think about this as collect the whole hierarchy. Instead of managing the hard drive and the memory all together, the goal of the buffer pool manager is everything above it will not be aware of the existence of the hard drive. That is, whenever you are accessing information, your view is, okay, it's always in memory. So essentially, the goal of the buffer pool manager is really try to make sure everything above it has the illusion that you have a very big piece of memory. So you will not worry about your hard drive. So essentially, if you talk about the interface that the buffer pool manager provide to the upper layer, it gives you the functionality to fetch a page, to update the page, so on and so forth. And all of this will be assumed is actually already inside memory. Now let's try to think about why it's hard to build that and what people do in database system to build it. So essentially, the buffer pool manager is actually acts as an intermediate layer between essentially the system and the disk manager. Okay? So in the bottom, you will have your hard drive and have a whole bunch of information being organized as a whole bunch of pages, which we know how to do at this moment. So here we have 4 different pages. And then in the middle, you have a DRAM, which is going to be smaller than your hard drive. Here, we are assuming our DRAM, for example, can only hold 2 pages. And then you have your buffer pool manager to really abstract away this hierarchical structure. Essentially, whenever the upper layer say, okay, I want the blue page, right? That's one request to your buffer manager. So the buffer manager, what buffer manager is going to do is going to say, okay, I will make sure this blue page is going to be in memory to answer your request. So what I'm going to do is actually try to check whether inside my DRAM there is this blue page or not. If there's a blue page, if there's no blue page, I will just fetch it from the hard drive, bring that page to my DRAM, and serve it. Okay? I will tell the whoever requesting the blue page to say, okay, in this memory buffer, slot number 1 is your blue page. I will make sure, unless you tell me to evict it, right? Unless you tell me you don't use it anymore, that page is there. Okay? And then, if there's another kind of request to say, okay, we want the red page, well, it's going to do the same thing, right? You're going to say, yeah, currently in the DRAM, I do not have this red page. What I'm going to do, I'm going to fetch it from the hard drive to my DRAM and serve it. Okay? I will tell whoever requesting it, it's a slot number 2 that you'll have. Use it. And then whoever requesting it will always have this information inside main memory. They will not know there's a hard drive. Okay? So that's the goal. And then what happens if there's another request come in to say, yeah, we want the yellow page. In this case, yeah, you start to see a problem because the yellow page is not in the DRAM, right? So I need to bring the yellow page from my hard drive to my DRAM. But my DRAM is very small, so there's no space anymore. So what the buffer manager is going to do is going to evict some of the pages. Okay? If you have updates on this page, it's going to also reflect all the updates on your hard drive. It's going to evict it to make space inside your memory, and then bring this yellow page from the hard drive to DRAM and serve it. So it's as simple as that. Okay? This is a functionality that we want to provide. More concretely, if you talk about a more precise interface that a buffer manager provides, this is a very simplistic view about what we are trying to implement. Essentially, right, this is one object for the buffer. To initiate the buffer, right, you need to say, yeah, this is the set of the buffer, right? So, and the function is provided to the upper layer is you can pin a page, right? Whenever you pin a page, right? So essentially what I'm going to say is, okay, I want that page in my buffer. I'm going to use that. That's the request that we talk about, okay? To pin a page. You can unpin a page is to say, yeah, I don't need that page anymore, okay? You can just do whatever you want. And then you can create a new page, you can free a page, right? You can flash a page to reflect all the updates you have. So this is the interface a buffer manager provides to the upper layer. So essentially, as you can see, it's actually provide the illusion that all your information is inside your main memory. So if you think about what are the design decisions we have in building a buffer manager, right? So essentially, the key design decision is whenever the buffer is full, because it's going to be full at some point because of the storage hierarchy. My memory is going to be smaller than my hard drive. There will be at some point, my buffer is full. So key design decision in building a buffer manager is actually how can I pick the page to evict when my buffer is full. And that is actually what people spend the last 50 years on. You really try to understand how to do that efficiently, right? What is the trade-off between different strategies of doing that? So that's also what we are going to focus on today. If you think about this fundamental question in building a buffer manager, that is, okay, so how can I pick the page to evict? There are actually two questions that we could study, given different assumptions about what we know. The first assumption, the first question is essentially, assuming I know about the future, I know about all the future access that you will have on your data, assuming I know that, what is the optimal way for me to evict the page? So that gives you essentially the upper bound of the performance in evicting a page. So second question is, okay, let's weaken our assumption a little bit. I don't know about the future, right? What should I do in practice if I know nothing about the future, or if I know only a little bit about the future? It turns out the first question is actually easier to study. If I know the future, if I know the future access pattern, there is an algorithm in 1966 actually gave you the optimal strategy about how to pick the page to evict. So it's actually not that simple, right? So the algorithm is here, and so people start to try to prove it's really optimal, right? So the original proof is actually very long, right? So, and if you are curious about why it's optimal, there's a 2-page proof that people have, I think 20 years ago, something like that. So it's very simple, okay? So here's how it works. Assuming you have this stream of access, okay? Because you know the future, okay? Like you know what's going to happen in the future. And at current 10 point, I'm actually at the third access, which is this blue thing, okay? I'm trying to read this blue page. Everything after it, on the right-hand side, is the future. Hasn't happened yet, but I know I will need those pages, okay? And the first 2 pages, the black one and the red one, they already happened, okay? And I have a 2-page buffer, and the buffer contains these 2 pages. Black page is in the buffer, red page is in the buffer. Now I'm accessing the third one. I need to pick something to evict, because I have a 2-page buffer, I need to make room for this blue page. So what I'm going to do to pick in the page to evict is by really try to, because I know the future, I actually know when the when the black page is going to be used. I know when the red page is going to be used. I evict the page that I'm going to use furthest in the future. Okay? Essentially here, in the future, I'm going to use the red page earlier than the black page. In this case, I'm going to actually evict the black page. So this actually gives you something that is probably optimal, right? So in evicting a page, it's very simple. So and sometimes it's actually useful, okay? So it's not that by assuming you know the future is too strong. It's actually sometimes it's useful. When I was doing my PhD at Wisconsin, we have this kind of weird problem, like in machine learning, that you have a very big graph, like a terabyte of graph. It's a bipartite graph, so you have a whole bunch of variables, a whole bunch of factors that are connected. And then because it's so big, like a couple terabyte, you want to do some machine learning sampling on it, you start to actually store that on your hard drive. But I know my access pattern. I know that I'm going to sequentially scan one side of the node, and every single time I scan the node, I'm going to bring all the neighbors in. So I know the access pattern, right? So you can actually just apply this optimal algorithm to give you something that's actually optimal in picking which page to evict. So it's like sometimes it's actually useful. But often in practice, in more cases, you actually do not have this access to the future. Okay? So what should you do in practice? In practice, right, so there are multiple strategies you can do, depending on your assumption on your workload. The most popular strategy is called LRU, least recently used. Essentially, for each page in the buffer pool, what you are going to do is going to keep track the time when it's last unpinned. Okay? The last time this page is used. So, and then whenever you need to evict something, you try to evict the page which has the oldest or the earliest time. You try to evict the page that is least recently used. Okay? That's why I call it RRU. It's a very common policy, probably the most popular used policy. Very intuitive, very simple. And it works well when you have those repeated access to those like popular pages. Okay, so if you do your kind of like do your master program here, right? So there's a course called One System Lab I'm teaching with Marcus. This actually also this semester. So essentially, whenever you have the process, we'll talk about it. Whenever you have essentially temporal kind of locality, right? You are going to use similar collection of pages again, and again. LRU is actually super, super powerful. Okay, so it's actually very simple, and we can actually try to reason about the behavior of this together. Right, so this is actually one RU algorithm. So the way to read it is you have this request, okay? So you have 10 different pages, okay? So assuming that we have the access pattern, I read the 0, 1, essentially I read blue, orange, and black, and then I go back to blue, something like this. So we can start to reason about this behavior, okay? So I have a 3-page buffer. Whenever you first request the blue page, yeah, you bring it in, right? You have one cache miss one buffer miss, because that page is not in the buffering to actually have one I/O. And then whenever you are reading the second page, the orange one, right, again, you bring that from your hard drive to the memory and to the CPU, right? And then you have the third request, which is the black one. Again, you check the buffer, right? You bring that from the hard drive to the DRAM, and you bring that to the CPU. And then when you need this, for example, the blue page again is actually in the buffer. You have one buffer hit. You don't need to move that. You just like from hard drive to DRAM. But whenever you need, for example, this purple one, what you are going to do is going to evict the page that's least recently used. In this case, it's going to be the orange one. You are going to evict the orange one, pull that from the DRAM back to the disk, and bring this purple one from disk to the DRAM and bring that to the CPU. So on and so forth. When you have the brown one, right, you also evict the black page because that is the least recently used in the buffer. You bring the brown one from the hard drive to the DRAM, and you bring that to the CPU, and that's it. And then you get the idea. Okay, so it's very simple. Okay? We only need the blue one. You have another hit, right? So this is a very simple illustration of RRU. Any questions so far about this strategy? Any questions? No? Okay. So it's a very powerful strategy, but it's also not perfect. Okay. So one thing that's interesting is when you have a different access pattern. Okay. For example, we are having this sequential access of pages. I have 10 different pages. The access pattern I have is I read the first page, then second, then third, then fourth page, so on and so forth. I do this sequential scan. So here's the behavior of that if you are doing RRU. Okay? So here you have this blue page, right? You bring that in, great. Then you have this orange one, because you are doing sequential access. You bring that in, it's fine. And then you have this black page, right? You bring that in. Whenever you do the red one, which one you are going to evict? You are going to evict the blue one, right? And then whenever you have the purple one, which one you are going to evict? Going to evict the orange one, right? This recently used. Whenever you have this, which is the next? Yeah, brown one, you evict the black one, right? So as you can see, this doesn't look too optimal, right? Because whenever I'm sequentially scan all those pages, I essentially touch all the other pages in the buffer. It's a pretty, I would say, called like disruptive strategy, right? So moving those pages around, like evicting all those pages, doesn't give me too much benefit, right? But because of the policy of RRU, I actually need to touch, pretty much evict all those pages in the buffer one by one, right? But again, it doesn't give me any benefit. I have the number of misses. If you look at that, it equals 10, right? When you have 10 different access, because sequential scan, there's nothing can save. So this could potentially cause a problem. And but on the other hand, RRU is also extremely powerful. Where's my cursor? Yeah, it's also very popular. It's also extremely powerful. So one you can prove, if you're curious, you can read this paper in the 70s, is RRU is actually at most twice as bad as optimal. Okay, if you count the I/O, right? So the number of misses on a hit is at most twice as bad as optimal if it is given twice the memory. Okay, so if you think about this, it's actually very strong. That is, what are the benefits that I can get by knowing the future? Essentially, the only thing I can get by knowing the future is I can decrease the amount of buffer, the amount of pages in my buffer by 2 times, and then I can be at most 2 times faster. And the RRU gave you that strategy, right? So it's actually a very powerful strategy, even theoretically, right? So there's actually decades of study about RRU. But there are other strategies, okay? Another strategy is called MRU, which is actually the opposite side of RRU. That is, you try to evict the page that is most recently used. Again, for each page in the buffer, you keep track the time that last time is unpinned. And then you replace the page with has the latest timestamp. So here's just like one example of MRU. We can go through this together, right? So essentially, like the same access pattern, right? You have the blue page, right? So the first 3 access here, because I have a 3-page buffer, is the same as RRU because I don't need to evict anything, right? I have the blue one, I have the orange one, and then I have this black one, right? So they are going to be arranged in this buffer. And then after the buffer is full, let's wait like 2 seconds for this to happen. As you can see, I/O can be very slow. So the next one is the blue page, right? It's actually in the buffer. So you have a 1 buffer hit. You just directly move that from DRAM to the CPU. And then the next one, I think, is the red one. And then instead of flashing out the blue one, you are going to flash out the, you're going to, you're going to flash out the blue one because that's most recently used, okay? So, and then whenever you have this, well, what's the next request? The brown one, right? What you are going to do, I think, to evict the purple one, I think. Yeah, because that's most recently used. so on and so forth. Okay? So this MRU. If you think about LRU and MRU, right? So it's sometimes useful to actually put them side by side and to see actually the difference of their behavior. So this is just one such example. Okay? So the same access pattern, but we have this MRU and LRU put in essentially side by side. Okay? So here I have repeated sequential access. Okay? I just do 0 to 9, and then I do 0 to 9. 5-page buffer. The left-hand side is LRU, the right-hand side is MRU. Okay? So not surprisingly, for the first 5 access, they're all the same. Well, because my buffer has half space, right? They're all the same. So interesting happens when you have this brown page. What would happen? Essentially, in the LRU, you are going to evict the blue one, but for the MRU, you are going to evict the first one. Okay? And then for the next one, for the purple one, for LRU, you have this sequential flooding thing. Okay? You need to actually touch this buffer from the right to the left and continue to evict it. But for the MRU, you are going to only touch that single page. You keep evict that single slot inside your buffer. And then what's powerful about MRU is when you start the second round of this sequential scan, when you read the blue page again, you can see for LRU, this blue page is not in the buffer, but for the MRU, the blue page is actually inside the buffer. Essentially, when you have this repeated sequential scan, you can actually see the difference between MRU and LRU, where MRU is going to give you more buffer hit. Okay? So this is just one such example. And then the trade-off between LRU and MRU is actually heavily depends on your workload. So this is another thing. Okay? So have another access pattern called the index scan. So here, the scan pattern will be weird. I don't do this sequential access. What I do is I have a tree. The blue one is the root of the tree. The orange and the black one is the first layer of the tree. What I'm going to do is I'm always going to the root. I always have the blue page, and then one of this orange or black page, and then I do another page. Okay? So this is a place, when you go back home, you can actually look at this animation yourself, this is a place where LRU is going to be more powerful than MRU. If you think about why, is in this case, your blue page is being frequently visited because that's the root. Okay? Every once in a while, I will have access to the blue page. And when that happens for LRU, this blue page highly likely will be inside your buffer because it's not the least recently used, okay? So giving a reasonable buffer size. But for MRU, it has a tendency to actually evict the blue page because you often use that. It's often the time the most recently used page. So in this case, when you have this temporal locality that some pages are being used frequently over time, you will start to see this LRU thing start to outperform MRU in terms of how many buffer hit that you are going to have. So this is just by putting them side by side, as you can see, the LRU actually now it actually have 18 access, the MRU only have 15, right? So you can also see the difference. So this is the trade-off between LRU and MRU. Any questions so far about these two different strategies? No? Okay. So in practice, inside a database, you have different access patterns. For example, you have this like sequential scan, right? You want to scan every single tuple inside a relation, right? You have this sequential scan pattern. You have this, for example, hierarchical index scan, right? You have a tree, right, of your tuples or pages. You always go from the root to the leaf, right? You have this index scan pattern. You could have this like random access pattern, right? You have a whole bunch of pages. You just do random things, right? So to access them, you could have this like nested loop. Always like go like repeated sequential scan, right? You have a whole bunch of those. For each of these different access pattern, right? You could actually try to reason about what type of eviction strategy that actually perform well for each of this. So there's also a fundamental difference between the buffer pool manager inside the database and also the buffer manager inside the operating system. Because in your operating system course, right, so we also talk about the buffer, right? So there's a file buffer, the file cache, right? So there's also something similar inside the operating system. If you compare actually these two, it's actually inside database, we have actually more information we can assume compared with the operating system. In database, we know what query the user is asking. On the other hand, I actually know the access pattern, right? So I actually can have more flexibility to reason about which strategy to actually use inside my database system. Compared with operating system, right, often they actually do not have such a strong assumption on the workload. And that is why in most of the file cache, most of them will just do LRU and call it a day, right? So this is actually because of different assumption on the workload, you start to have a different design inside your system. And in principle, right, here we talk about LRU, MRU, right? So there are other strategies. People spend the last half a century to actually try to design different strategies. So just give you one example about another thing. There's one paper really like maybe 30 years ago called dbmin, right? So the observation is, okay, so there are many concurrent queries inside your database because there are many different concurrent users using that. And each query is composed of a collection of operators, and you could allocate memory for each of these operators of each of this query, and then use different replacement strategy for those different operators. For example, assume you have this single database buffer pool, right? And you have, for example, 3 different operators that you know people are running. You have the sequential scan of a relation T, right? In this case, you could say, yeah, so I actually gave you these 4 different pages inside my buffer, and then I'm going to use MRU for that because I know you are going to do sequential scan, right? That's performed well. Another operator is, for example, someone is running index scan, right? I could say, okay, so I gave you another chunk of buffer, right? Do not evict the blue one because someone else is using that. You have the green one because I know you are doing index scan, right? There's a temporal dependency. Temporal locality, right? Essentially, I will use LRU for that collection of pages in my buffer. So this is another kind of very popular strategy inside database that people do. Because I know how you are going to use or access your data, I can actually try to give you a better replacement strategy for each of your workload. So there's a lot of research going into this in the last half a century, right? So in this course, we just scratch the surface, we talk about LRU and MRU, and potentially some hybrid way of combining this. So buffer management sounds very simple if you just think about that LRU, but there are actually a lot of detail going into this. One thing that's interesting is to compare that with the operating system, right? So you have the buffer inside the database, you have another buffer inside your operating system. Right? Again, we talk about this, right? So the database has more assumptions, so it can actually try to reason about different strategies. For operating system, sometimes it doesn't have the luxury of knowing what people are going to do in the future, right? Because it's operating system, right? So sometimes it has less flexibility or less information in picking this. But what's become interesting, if you think about this, now I have, if you're not being careful, you have these 2 different buffers, right? Because my pages is a whole bunch of files. Whenever the database tries to access the file, fetch a page, you need to go through the file buffer, file cache of the operating system. And then you actually have these 2 buffers. If you are building a database system and the operating system separately, which is what people often do today. So when you have these 2 buffers, so it's actually become kind of interesting, okay? So just to show you, there could be interesting when you're dealing with buffer management. So this is just one animation about this. So assuming you have this database buffer, okay, holding the blue page at this moment, and you have this file cache in your operating system, currently holding the red page. And then inside your hard drive, you have these 3 different pages. So assuming the database say, okay, so what I want to do is to evict the, where's my mouse cursor? Yeah. So assuming the thing that you want to do is to say, okay, I want the orange page. That's what database want to do. In this case, right, so it's going to tell the database buffer, not the file cache, okay? So the database system doesn't have access to that. To say, okay, I want orange page. And then what system going to do? Okay, so okay, I don't really have a choice. I need to evict the blue one from my database buffer to my hard drive. But because the database is using the file system, the way the database is going to tell the system to do it is actually to tell the operating system to say, okay, here is the blue thing. I want you to update your file, to put that back. And then the operating system is going to get that request. If you think about what the operating system is going to do, it's actually going to bring this blue page from the disk to the buffer. Okay? So that part needs to happen. And then evict that from the file cache to the disk. So essentially, you have this interaction between these two different buffers. And sometimes when you have a small buffer, for example, you have one page in the database buffer, one page in the file cache, for example, and then you say, yeah, I want the orange one. The database will say, okay, I want to evict this blue one. So what the operating system need to do is to actually bring this blue page from the disk to the file cache to make sure I can update it and then flash it back. But because my file buffer is too small, the system actually need to also evict this right page inside the file buffer back to the disk, bring this blue page from the disk to the file buffer, and then update it. So as you can see, when you are building these two different systems independently, when you have these two different buffers, their interaction could be pretty interesting, right? If you are not being careful, you could be paying a whole bunch of IOs that you don't have to pay if you manage a single buffer yourself. So this actually goes to a very interesting research topic people have today. It's actually how to co-design this operating system and database system together. Historically, right, they are actually built kind of not completely separately, but they are two different computer systems that interact with each other. And now people start to think about, yeah, what if I build them all together to really get rid of problems like this when you have these different buffers interacting with each other. So that's about buffer manager. Okay? So now, if you are building a system, once you have this buffer manager, you can actually assume all your data are inside your memory, and then you can start to move essentially one layer up. You can start to think about, okay, given the buffer manager, how can I access my data? And let's go to the access master layer. Yeah.
Regarding the operating system
Yeah.
buffer, like lots of programs just use the operating system buffer. They don't have their own buffer.
Yeah.
Why can't the database system just use the operating system eviction policies?
Oh yeah, I mean, you could, right? So like in fact, many database systems today actually do that. Yeah. So if you do SQLite, right? So I'm sure it doesn't have its own buffer, just use a file buffer, I think. But essentially, at least historically, the file system buffer doesn't give you too much flexibility in managing it. For example, if I want to do dbmin, if I say, okay, I want to allocate this 10% of my buffer for this query, 90% for that query, because I know what's going on. I want to use RRU here, I want to use MRU there. The file system, there's nothing stop it from doing that. But historically, doesn't give you that flexibility, right? Because in database, I actually know more about my workload. Potentially, I could do better, right? At least historically, that's the view from the database community, right? People start to revisit it because RRU often is not that bad, and then hardware has become faster, right? So the speed of hardware become faster, right? The trade-off and the start to shift you will probably see different designs, like down the road, some system will actually rely more heavily on the file system buffer. But here we are talking about, this is designed like 1980, something like this, that we are going to talk about. At that time, you don't have that luxury of, at that time, I would say, I always even bigger bottleneck compared with today. You actually want to have more flexibility in managing those buffers. Yeah. Okay? Any other questions before we move one layer up? Once we move up, we cannot go down again. Okay? So any questions about the buffer? No? Okay. Now let's move one layer up. What do we want? So now we know how to pin page in the buffer. What we want to do is to really provide a whole bunch of access methods on your data. What do we mean by that? Essentially, we say, yeah, here's a relation. I know they are organized as a collection of pages, a collection of tuples. But the thing I want to provide is how you can access those data. I don't want to give you this full access to all the data there. I want you to follow certain pattern. For example, you can say, yeah, I want you to sequentially scan all the tuples. That's one access method that you can have on this relation. You can build maybe a B tree, that we're going to talk about today, over that relation to make sure you can actually look up those tuples. You can do access this information using a B tree index. Okay? You can have a hash table. You can access the information in the hash table. You can sort it. Okay? That's another access method. You can sort the data. So I give you this high-level operations, sub-operators, actually operators, that you can do over your data to make sure whenever you are implementing these relational algebra operators, like drawing or selection, you can actually use those access methods instead of fetching tuples by yourself. This is actually like another layers of abstraction for you to access the data. So that is what we want to provide. Essentially, the interface to the upper layer at this higher level of abstractions to actually access information in a table without interacting with the buffer, without interacting with the hard drive. All the upper layer will not talk to the buffer. Okay? They will actually only use this collection of access method to access information. And that is where we get this flexibility in optimizing those access. That is how the user give you that piece of information to the buffer pool manager. If you give the user the full flexibility in accessing their data, there's no way the buffer pool manager can actually know the access pattern. So that's the secret sauce. That's why we want this higher level of abstractions. So what do we have? Essentially, you have this relation, and then it's actually mapped it to a whole bunch of pages on your hard drive. We talked about it on Wednesday. And now we have this buffer manager to actually serve all those requests of accessing those pages. Whenever you have access method, for every single access method, for example, sequential scan, okay, it's going to be translated into a sequence of calls, invocations to the buffer manager. So let's look at a simple access method that is sequential scan. Okay, I have a whole bunch of things. I want to find the tuple whose attribute x equals to y. Okay, this is one access method that I have. Essentially, when you are writing a SQL query like that, this is actually the access method that you are going to use. I could do that using sequential scan. Okay, so essentially, if you're doing this, what you are going to tell the buffer manager is to say, okay, give me page 1 of this relation. And buffer manager is going to say, okay, here they are in the first slot in the buffer. And then I'm going to, because I know it's in the memory, I'm going to go through inside the memory every single tuple in that page in the access method layer, and I will check whether the attribute x equals to y. If that's true, I will return it. Otherwise, yeah, I move on. Once I finish it, I will tell the buffer manager, okay, now you can unpin the page. I don't need that anymore. Give me the second page. And then I'm going to scan all the tuples and check, give me the third page, so on and so forth. This is the interaction between the access method and a buffer manager. Okay? If you think about the cost, think about what the cost is, the I/O cost, and take a break, and we'll talk about that in 15 minutes. Okay, so let's get started. Can people on Zoom hear me? Give me a signal. Okay, perfect. Yeah, so this is a very simple example of one access pattern, which is sequential scan. Okay, so the way I interact with my buffer is I keep asking pages one by one sequentially. So what would be the cost, right? So in this case, assuming, this is read only, right? So assuming the pages are sequentially allocated on my hard drive, right? So what would be the I/O cost for this? Well, assuming I have D different pages, right? So the thing I'm going to do is, because they're sequentially allocated on my hard drive, I pay a single unit of seek and rotate, and then I pay D unit of transfer, okay? So this is the I/O cost of this. Assuming the pages are randomly allocated on the hard drive, which could happen, the cost you are going to pay is you have a D unit, right, of the seek and transfer, because for every single page, you need to rotate the arm, rotate the arm and rotate the disk, right, to find the right place, and then read it. So we have D unit of this seek and transfer, and then have D unit, like seek and rotate, and then have D unit of those transfer. And then when you update your tuples during scan, that's also something you can do in this access pattern. You need to write back the updates, and then you pay one more of the transfer per page. So the question is actually, for this functionality, that is, we want to find tuples with certain property that, for example, attribute x equals to y. Can we do better than this, right? If you look at this cost, it's pretty expensive, right? So when you have a terabyte of information inside your relation, you need to bring that terabyte from the hard drive to the DRAM, right? So sometimes you can get at most depending on how crazy the machine you have, but 1 gigabyte per second is actually pretty fast in many machines, right? So, and just talk about 1 terabyte of information, that's 1,000 seconds, right? It's very slow to just find a single tuple. So can we do better? So yes, right? So you could have some data structure called index, right, to really help you. So the way to think about index is essentially you can build that over this relation. You can build a B tree, you can build a hash table to help you to do the lookup. The modern way to think about what index really is, it's pretty much it's just a function. The signature of the function is this. It takes as input essentially a predicate. For example, the age equals to 5. I take as the predicate and try to map it to a record ID, okay? To the ID of the record, which is the combination of the page ID and the slot ID, right, that satisfy this condition. So all you are trying to do is to design this data structure such that you can comprise this function f as much as possible. So that is the view of what index really is. It's nothing more than a compressed representation of this mapping function. So once you take this view, right, there are so many things you can do in designing this function. There is the traditional way, right? You can build a tree index, right? So you can build a hash table, or you can even automatically learn that function. There's nothing stop you from training a neural network in some machine learning model to just learn that function. So this is the view of index. So in this course, we are going to talk 2 different, more traditional indices. One is the B tree, another is hash table. So today, let's start from B tree. This is one of the most important data structure in database system. Essentially, a B plus tree, or B tree, sometimes, so in this course, we are going to talk about B plus tree, but very similar to a B tree, and So a B plus tree is a self-balancing tree data structure that actually try to keep the data sorted. Whenever you have a search, insertion, and deletion on the B plus tree, n is number of tuples. You have log n in the big O sense for each of these operations. It's pretty much a generalization of a binary tree, which I'm sure you know pretty well. it's a generational binary tree in which each node is going to contain actually more than 2 children. Okay, it's going to have a whole bunch of those. It's actually try to optimize for I/O. So because when you're building a binary search tree, you are actually assuming that data structure actually fit into memory, right? Every single cache line, I mean, it's like 256 byte, for example, right? So that's the granularity you are doing. Whenever you are doing this database thing, right? So every single data access is a single page, right? You cannot need to deal with that. So it's a design for I/O as a generalization of the binary search tree. So essentially, given this relation, okay, on the left-hand side, have a whole bunch of tuples. The way to build a B+ tree is the thing on the right-hand side. It's alternative to the heap file. Okay, it's still like a file. If you think about the SQLite, that pretty much the whole database is actually B+ tree. It contains a whole bunch of pages. That doesn't change. Okay, it's just a different organization of your data. So you have a whole bunch of pages, and then you form a tree of those pages. Every single node in the tree is a page. And then there are different designs of this B+ tree. One design is for the leaf node, you actually store the whole bunch of pointers, like the record ID, which is a pair of page ID and slot ID of the corresponding tuple. And then you try to form a search tree like this. So essentially, the B+ tree is an M-way search tree. It's perfect balanced. So every inner node is a page. Okay? So need to be at least half full, okay? Because, to make sure it's balanced. And every inner node is a page, and that page can contain multiple keys because it's a page. Right? Could be 4 kilobytes, something like that. If you have k different keys in that page, then you are going to have k+1 children of that page. And then you have this recursive structure. If you are familiar with a binary search tree, right, so this data structure should be very easy to understand. It's simply, for every single node in the tree, you have more than 1 children, simply because I have a page. I could store more information. It has some constraint to make sure it's always balanced. So each node is a page. There are 2 different types of B+ tree. The first type is called unclustered B+ tree. In this case, for your leaf node, for that page, you are storing the pointer, the record ID of the corresponding tuple. So another alternative is you could have something called clustered B+ tree. Essentially, if you look at the leaf node, instead of storing all those pointers or like a record ID, you actually put the actual data into the leaf node. So this is called clustered B+ tree. There's 2 different alternatives. When the whole thing is unclustered, you are storing the record ID. When the whole thing is clustered, you're actually putting real data into the leaf node. So the consequence of this is you could have actually 1 clustered B+ tree for each relation, because I cannot have 2 different clustered B+ tree on different attributes, because then I'm going to duplicate my data, because every single clustered B+ tree is going to put the real data there. I can only have 1 clustered B+ tree for every single relation. I could have a whole bunch of unclustered B+ tree for the same relation, because all I'm storing is the pointer. Okay, makes sense? There's a clustered, there's unclustered. Once you have this data structure built over your relation, you could provide a whole bunch of interesting access methods. For example, you can say, yeah, so I can do a point query lookup on B+ tree. I can say, yeah, once I have B+ tree, one thing I can do is I can find a single key. I say, yeah, give me all the tuples with age equals to 5, for example. That's one access method you can provide. So assuming your node size is m, okay, and your number of tuples in the relation is n, okay? So what is the cost of doing this? Essentially, when the size of the node is m, so assuming so assuming you can hold m keys, right? So in that case, how deep the tree is, right? We will have n different tuples. So in this case, right, you are going to have this log mn, right, which is the depth of the tree. And whenever you have this point query, the thing you are going to do is going to start from the root, that page, and you try to find the right child, and then you do this. Essentially, the number of I/O that you have for unclustered B plus tree is going to be the following: that you are going to try to find the right leaf node, which in the worst case, if the buffer is cold, the buffer is empty in the beginning, is you are going to have log mn, number of I/O, to find the right leaf node. And then you get a pointer, which is the record ID, and then you fetch it. Essentially, if you have an unclustered B plus tree, the cost of answering this query, right, of supporting this access method is actually log mn plus 1. Okay? So log mn is you read one page per level of the tree, and then you read the actual tuple plus 1. Whenever you have a cluster B plus tree, right, the thing that you are going to have is this, right? You can just essentially try to reach the leaf node. Then you have your actual tuple there. You do not need to find fetch the actual tuple because I'm storing the actual information in the leaf node of this cluster B plus tree. Okay, so often the case that when the n number of tuples is big enough, you will have the B plus tree. Both of this will be much faster than sequential scan, right? So that's very clear to see if you are counting number of IOs. Okay? And you could support different access method. For example, you could support range query. You can say, yeah, give me all the tuples in the range age between 5 and 10, for example. Right? That's another access method that you could have. Assuming you have the node size equals m, tuple, a number of tuple equals to n, right? What would be the cost of supporting this access method? We have the depth of the tree is still log mn, right? So when you have an unclustered B plus tree, what would you have? Well, you are going to find the first leaf node, which is the lower bound of the range, and then you are going to scan the leaf node until you find the upper bound. And then for each of the tuple contained in those leaf nodes, you are going to fetch the actual tuple. Okay? In the worst case, all those fetching of actual tuple, each one of them will incur 1 I/O. Because in the worst case, those tuples could be stored in a random way inside your actual relation in the unclustered B plus tree. In this case, this is the cost, right? So the first term, right, log mn, is try to find the leaf node of the lower bound. Okay? And then the second term, right, number of tuples over tuple per page, right? So this is for each of so number of tuples, right? So is how many tuples you are going to have in this range, over how many tuples you can store the pointers inside each leaf node, right? So the second term is the number of leaf nodes, those pages you are going to scan, you are going to fetch. And then the third term is actually, in the worst case, every single tuple I'm returning, I need to fetch the actual data. And in the worst case, those data are going to be scattered inside my relation that every single tuple I need to fetch, I incur another I/O. So this is the worst case cost of supporting this access method using unclustered B plus tree. When you have a cluster B plus tree, right, what would you have? In this case again, right, I need to find the lower bound, the leaf node, and then I'm going to sequentially scan. No, sorry, not sequentially. So I'm going to scan. Well, in B plus tree, often sequentially, yeah, but it doesn't have to. I'm going to scan the leaf node because I have the actual data. I don't need to fetch it. All I need to do is to just scan the leaf node until I reach the upper bound, and then I have the tuple. So cost will be like this, right? You have the log mn, the first term, which is try to find the lower bound leaf node, and then the second term, number of tuples or tuple per page, right? It's number of leaf nodes that you need to fetch. If you compare these two costs, you can see it's actually not clear which one is faster, to be honest. The first thing, unclustered B-plus tree, right? You have this additional third term that's for every single tuple I need to fetch something. But on the other hand, I also have that for the unclustered B-plus tree, because my leaf node doesn't contain actual information, I can actually put more tuples in the same leaf node. So the tuple per page for the unclustered B-plus tree is going to be larger than the tuple per page of the clustered B-plus tree. Which one makes sense actually depends on how many tuples that I'm expecting from this access method. If I have an access method, so if I have one query that has very big range, that's going to cover all the tuples, then clearly, right, so the cluster B-plus tree is going to be faster, right? So, but on the other hand, it doesn't have to, right? So when the range is a little bit smaller, right, so it's not really clear like which one is faster. So the beauty of a database system is this is not the user should worry about. The database is going to, next week or the week after, we are going to talk about something called cadenated estimation, where the database try to estimate how many tuples that you are expecting, and then try to reason about all of this cost. So at this moment, it's very important to get on the same page about those cost model. And then down the road, we are going to think about how database automatically pick the best strategy using those cost model. So you can have other access methods. You could do insertion into B-plus tree, right? So in this case, for example, you can say, yeah, so this access method, you insert a tuple where age equals 5, right? So the algorithm to do that is actually you try to find the right leaf node corresponding to age equals to 5. And then you put data in this leaf node L. Of course, when there are space in the leaf node, empty slot, you just put it in, you're done. What's going to be a little bit more complex is when L is full, then what should you do? And then you try to split this L, okay? So, and then you have these two different leaf nodes, and then you insert the key, additional key separating these two leaf nodes back to the parent of L, and you continue to do this recursively until you can actually do not need to split anymore. So now let's look at one example, okay? So it's going to be very clear what's going to happen here. So when you go back home, it's also interesting to actually play with it, right? So it's very simple. I mean, after you kind of play with it. So essentially, assuming right now my database is empty, and then I insert, for example, one tuple, which is, for example, 31, right? If you do this, you are going to have a single page, contains 31, okay? So it's very simple. And then you have another, for example, 41. In this case, what you are going to do, I have one node in my tree, which contains 31. My max degree is 3, okay? So every single node can hold 2 keys, okay? So I will first find that page. Because I have one page, I don't have a choice. I mean, it's that page. And let's say, yeah, so I have one empty slot in that page. I can just put 41 there. So it's very clear to see what happened. You find the page, you put that in, done, okay? And then you insert maybe another one, like 37. So what's going to happen is, okay, I find the right page. I find that page. I only have one page. It's that page I'm going to find. I try to put 37 into that page. But because that page can only hold 2 numbers, I need to split it. Okay? In this case, I'm going to have a one page with 1 number, one page with 2 numbers. Okay? And then you have 2 nodes, and then you try to insert the key separating these 2 things, 2 different pages, into the parent node. So once you insert 37, you are going to have 2 different levels. Okay? You have 1 root node and 2 leaf nodes. And this is what's going to happen. You find the page, you insert, you split. Okay? Now you have 2 leaf nodes, and then you have 1 root. So far, so good, right? Any questions? No? Okay. So you can continue to do this. For example, insert 100, get a little bit more interesting. What would you get? In this case, right? So it's a search tree, right? You look at the root, it's 37, 100 is bigger than that, so it's going to the right child. And then you say, yeah, I'm going to insert that to the right child. Now it's full. I split it. And then I insert the separator to the root. Because my root only has one thing, I do not need to split the root. I can have two-level tree where there are two keys in the root, and then I have 3 different leaf nodes. I will have something that look at. I find the right thing, split, and insert the separator into the root. And then you can insert, for example, another one, like 9, right? So it's the same. You are going to actually insert that to this node, right? And then do not need to split, something like this. We'll have like 91. That becomes a little bit interesting because you want to insert 91 to the third leaf node on the right-hand side. And then you are going to split it. You insert a separator into the root, and then your root has 3 different keys. You cannot hold that anymore. You also split the root. You introduce another level. Okay? So after you insert 91, you are going to have something that looks like this. Okay? So it's as simple as that. Any questions? It's clear? Okay. So another access method you can do is you can do deletion in the B-plus tree, right? So essentially, the thing you need to do is, delete a tuple. What would you do? You first find the right leaf node containing the tuple that you want to delete, and you remove it. So the only thing I need to be careful about is we want our B-plus tree to be balanced. Okay? You cannot have a leaf node that's not that full. Okay? Every single node need to be at least half full. Okay? So in this case, what I'm going to do is, if this node is at least half full, you are done. Great. Otherwise, you start to merge 2 different leaf nodes, or you try to borrow tuples from your neighbors and update your parents. Okay? So different systems will do different strategy, right? But essentially, this is what you need to do to make sure every single page is at least half full to make sure the whole thing is perfectly balanced. And we can look at some example together to really get the same page about what we are talking about. So let's go back to essentially, what happened? Let's take this tree that we already have. And then let's try to delete 31. Okay? So in this case, I need to delete 31. So in this case, what would I have, right? So the first thing you are going to do is you are going to find 31 in this tree. In this case, it's going to be in the first leaf node. And then you are going to try to remove it. Okay? And you try to check whether you need to merge those 2 different pages or not. In this case, you don't have to, right? You can just delete it. You have fun. And then you can say, then let's delete another thing. Let's delete, for example, this 41. So this one got a little bit interesting. So you first find 41, which is in the middle, and then you delete that. Once you delete that, the leaf node is actually empty. Okay? And then you also need to try to delete that, in the parent, I think. Let's see what it does, right? So it's kind of find that page, remove it, right? And then try to actually rebalance the tree by actually, in this case, actually split the leaf node on the right-hand side. You continue to do this. It's actually very, very natural. If you want a precise algorithm about what it's doing, so there's a very, very precise one in the textbook. It's actually not that long. Okay? So this is just make sure you get the intuition. Okay? The goal of insertion is to make sure, insertion and deletion is to make sure the tree is still balanced. Okay? So that's the goal. Okay. So in practice, B+ tree is actually a super, super powerful index. And you can actually see that. So in practice, it's often the case, right? So each page could be pretty big, okay? For example, it's not rare for you to see, for example, the every single node contains maybe 200 keys, like 8 kilobyte page, okay, something like that. I mean, that's not too rare. Assuming you have those 8 kilobyte page for each node. So often it can hold, for example, 200 keys, right? And in practice, often the fill factor, right, how full each page is, is at least 50%, but in practice, often, for example, like 60%, something like this. Right? In this case, assuming these two different constants, what you are going to have, the fan out of each node, how many children that each node have, will be like 130, something like that, like in this case. And then the capacity of the tree, how many tuples that you can actually hold by having this tree. When you have 4 different levels of the tree, the depth equals 4. If the fan out is 134 in this case, right? So you are able to hold with a 4-level tree 300 million entries, okay, in this case. When you have this fan out, when you have this page size, which is actually very small in practice, to be honest. And then if you think about the pages per level, okay? So first level of the tree has a single page, right? That's root, right? That's 8 kilobyte. The second level going to have just like 134 pages, right? So that's our assumed fan out, right? That's like 1 megabyte, okay? So that's fit into your register of your CPU, okay? And then the third level, right? So it's going to be 140 megabyte, right? That fit into the memory of your phone, okay? It's super small, okay? So, and then if you think about this, what is the number of I/O you need to actually fetch the tuple? Well, in this case, if you have a buffer manager, right? Today's computer, right, like that laptop has like 32 gigabyte of memory, right? So it's very easy to hold all these 3 different first levels of the tree into my memory because all I need to hold is like 150 megabyte, okay? So that's fit into a Raspberry Pi very easily, okay? So that probably fit into your coffee machine, to be honest, yeah. So you have the 150 megabyte of things fit into your buffer. And then whenever you are fetching the leaf node, you are incurring actually 1 I/O just for the first layer because all the other layers are already in the memory, right? To actually try to fetch it, you only need a single I/O, and this gives you a capacity of using a single I/O to query 300 million tuples. Okay? So this is the power of B-plus tree. In practice, it's a super, super powerful data structure. But on the other hand, like pretty much everything in building systems, there's trade-off. Now we have this B-plus tree. Now we have sequential scan. Let's try to reason about which one is better. So far, if you look at this cost model, one thing that you might think about is, yeah, B-plus tree is super good. It probably dominates the sequential scan. But that's not the case, because there's a caveat. Essentially, if you look at even finer ground access pattern, sequential scan is sequential, right? As the name implied, right? So it's sequential scan. But whenever you have this B-plus tree stuff, you are actually talking about a random access, not a sequential access. Because all those nodes, they are actually scattered in your memory. Whenever I'm going from the root to the leaf of the tree, right? So I actually have random access, not sequential access. And on today's hardware, right, sequential access could be much, much faster than random access. So that is why, in practice, it's not always the case that B-plus tree is going to dominate sequential scan. Sequential scan is also super powerful and going to become actually even more powerful day by day. So when you organize your relation as a heap file, right, so you have a lot of sequential scans over the file. Whenever you have B-plus tree, you have a smaller number of random access. But sequential scan is faster than the random access, so which one is better depends on this ratio. Okay? So the performance ratio between sequential access and random access, and also how many access that you are going to have for each of this data structure. Sequential access is super faster. It's true for disk, true for memory. And the trade-off between this is actually super, super interesting. And whenever you have a new generation of storage, people need to revisit this. So it's not really, we shouldn't take for granted that, I mean, it's not always the case that bpass3 is always faster. Okay? So that's actually one assumption that you need to revisit for every single generation of your hardware. And also for every single workload that you have. So, and you can optimize both. Okay? For sequential access, you can do those perfection type of thing, right? For like sequential scan, you can also use a whole bunch of hardware instructions like SIMD, those type of things, to really speed it up. But on the other hand, it could be a little bit hard to do for bpass3, but there's also other optimizations you can do. So concretely, right, if you look at these two different queries, the first query say, yeah, so select, I want to find a tuple where a equals 5. The other tuple, the other thing is a range thing. I want to find all the tuples within that range. Right? It's a very big range. Like the range is between 0 to whatever, like 100 billion, whatever, right? A big range. If you look at these two queries and try to think about which one could be faster, should I use a B tree? Should I do a sequential scan to find the tuple? Because both things can give you that. So the way to think about it, which we are going to do that exercise in the next couple of lectures when we talk about query optimizer, is really try to write down the cost model and try to reason about it. Right? In this case, intuitively, right, probably for Q1, we might want to use a bpass3, right? Because highly likely, right, you are not going to fetch too many tuples, right? In that case, it should be fine. It's not that huge amount of random access, even if it's unclustered, right? So you need to find one leaf node, and for every single tuple that you have, you fetch them, right? So probably for Q1, I mean, there could be a case that Q1 you want to sequential scan. For example, all the tuple have a equals to 5, right? So then you sequential scan, right? So in the database, it's going to try to estimate how many tuple going to return, and then try to pick that for you. Okay? But as you can see, even for Q1, there could exist a database instance that sequential scan is faster. Okay? And then for Q2, right, probably, right, if the range is very big, if it covers a whole bunch of tuples, maybe you should actually use sequential scan, right? Because sequential access is super fast. And also when you have those unclustered bpass3, if you need to access every single tuple, the number of I/O you are going to have is what? Equals the number of tuples you have. Because every single tuple in the worst case, you need to hit one different page, right? But for sequential scan, the amount of I/O, if you need to fetch all the tuples, equals the number of tuples over the number of tuples you can hold for page, like for each single page, right? So in this case, if you need to fetch a whole bunch of tuples, sequential scan actually can save you I/O. Okay? As you can see, the called selectivity, which is going to be very precise down the road, the selectivity of your query is a fundamental factor inside the database system for you to pick which strategy that actually works better. And we are going to talk about how to estimate selectivity, I think maybe next week or week after, and also how to automatically pick this automatically. So there are more about bpass3, right? So people have been working on that also for more than half a century, right? It's a very deep area. If you're interested, there's a whole book about it, about bpass3. So today, right, so there are a lot of things to reason, right? So one thing to reason about is what is the optimal node size, okay? So how big that page is. So essentially, intuitively, the slower the disk, the larger the optimal node size, right? Because the more expensive the I/O is, the more benefit you can get by making the tree a little bit shallower, okay? Intuitively, like essentially, the optimal node size is a function of how slow your I/O really is. So in practice, when you have your hard drive, right? So it's not very rare in practice people have a node size like 1 megabyte, something like that. When you have your SSD, right? So that node size starts to become a little bit like smaller. When you have those in-memory database, you have a kind of very small node, okay? So optimal size also varies on workload, right? So whether you want more scans, whether you have more point queries, right? So, and some database system, when they delete tuples, sometimes they delay the merge of the node. So they will allow some of the node that's not half full, right? So and try to delay that. So that's also possible, right? Reduce the amount of reorganization, and they periodically rebuild the tree. So, and there are a lot more, okay? You can support the variable, length keys, non-unique keys, all the type of things, right? So, but intuition is the same. We want to build a tree structure over my data to make sure every single time I try to find a tuple, I can do that in log time. So another thing that's interesting is assuming I have a relation, and I want to build a B plus tree, how should I do that? Right? So there are two different ways that you can do it. The first way is kind of slow. That is, for every single tuple inside a relation, you insert that one by one into the tree. Okay? You could do that, and there's nothing stop you from doing that, right? So, but the problem of that is going to be very slow, because for every single tuple I insert to the tree, I need to find a leaf node, I need to insert it, maybe I need to split the leaf node and update my parent, split again, all the type of things, right? It could be very slow. There's a much faster way of building a B plus tree if you have your data ready. Essentially, you sort your data. For example, you have these 6 different tuples. The thing you do is you sort it, and then you can say, yeah, you construct a tree in a bottom-up way. Okay? Assuming every single of your leaf node can hold 3 different tuples. You can say, 2 different tuples in this example. You can have to say, yeah, the first 2 will be the first page, the third and the first one will be the second page. Then I have these 3 different pages in the leaf, and then I build that from a bottom-up way. Then I insert another parent to connect them. So often, this is faster. Okay? In PostgreSQL, right? So this is something you can do. You can just give it a relation. You can create an index over that relation using this SQL statement. And then sometimes if you do not specify whether you are building a B tree or whether you're building a different type of index, by default, if you build a B tree for you, you can build a cluster B tree. You can only have one of those for one relation because it's going to reorganize your data. You can build a whole bunch of unclustered B tree on your relation by using this. So this is a B plus tree. Okay? So another thing is, yeah, can we do even better than B plus tree, right? At least for point queries, right? For single attribute match. In this case, we have this log overhead from the B plus tree, right? Can we just push that into constant? So the way to do that is by building the data structure called a hash table. And that's something we are going to talk about on Wednesday. Okay? So that's all for today. We are a little bit early. But next time, we are going to continue to talk about access method, hash table, other type of things. Okay? So that's all for today. I'll see you guys on Wednesday.